Hi, my name is Zainasan and my group members are Shafi Iqbal, Syed Ibrahim Ali Haider and Omama Rizwan. The topic we have today is Euler's formula. Looking at the contents of the presentation, we have Introduction to Euler's formula, planar and non-planar graphs, formula testing with examples, a proof, followed by some applications. In the next slide, we have Leonhard Euler, the Swiss mathematician behind the idea of Euler's formula. What is Euler's formula? Let's read the theorem. Let G be a connected planar simple graph with E edges, V vertices, and let R be the number of regions. The formula is pretty simple. We add up the regions and vertices and subtract the edges, and the answer should always be 2. The theorem has a term planar, and you must be curious to know what planar is. On the right hand side of the slide, I have planar and non planar graphs. Non planar graphs are one that have cross edging between them. If you take a look at the top left graph, it has cross edging between them, but we can change this particular graph into a planar graph simply by removing one inside edge and connecting it from outside. The middle diagram in the top part is a planar graph that is changed from the left one. Below you can see some non-planar graphs on which Euler's formula cannot be applied. As far as planar graphs are concerned, we can use the formula r plus v minus e is equal to 2. And if it's true, then we can say that Euler's formula is applicable on the specific graph. Now my partner Ibrahim Ali is going to show you some working with the formula.
Now we'll move on to test some examples using Euler's formula. As stated by Zen, Euler's formula is r plus v minus e equals to 2, where r are the regions, number of regions, v are the number of vertices, and e are the number of edges. So over here we'll take simple planar graphs, and as we can see on our left side, we have a diagram that has vertices A, B, C, D, and E. And now in this simple planar graph, we have a total of 4 regions. Our first region being triangle CDE, and we'll label this as R1. Our second region being BCE, we'll name this as R2. The third region being ABE, R3, and finally our fourth region, which is our outermost region, will be R4. So the total number of regions we have are 4. The number of vertices that we have are 5, A, B, C, D, and E. And the number of edges as we count are 7, one from A to B, then A to E, B to E, B to C, C to E, E to D, and then finally D to C. Moving on, if you apply the formula that r plus v minus e equal to 7, so we can see that 4 plus 5 equals to 9, and 9 minus 7 definitely equals to 2. Then moving on to the next example, we have we then have again 3 regions: R1, which is triangle ABC, R2, which is triangle CDB, and the outermost region, which consists of all the other regions. So we have a total of 3 regions. Moving on, we have a total of 5 vertices, which include A, B, C, D, and E. And the total number of edges are 6. And again, when we apply Euler's formula, we get 3 regions plus 5 vertices minus 6 edges gives us 2. So again, Euler's formula is proved to be true. Then when we take our third example, we have a total of 6 regions. R1 being AEFB, R2 ADHE, R3 EHFG, R4 BFGC, R5 HDGC, and finally R6 being the outermost region. So a total of 6 regions. Then when we count all the vertices A, B, C, D, E, F, G, H, we have 8 vertices. And when we count the total number of edges, they are 12. And on applying Euler's formula, we get 6. When we add 6 plus 8 and then subtract 12 from it, we get 2. So once again, Euler's formula has proved to be true. As we saw by applying Euler's formula on our examples, we always got 2 as our answer. But we have to prove that how this Euler's formula works. So moving on, Shafe will explain the two proofs.
Now let us look at proofs for Euler's formula. In proof number 1, we assume the graph G to be a tree. Which can be seen on the right, we see that the number of vertices is 6, the number of edges is 5, and the region is 1. As trees are inherently acyclic in nature, that means that they do not contain any cycles and do not contain any interconnected edges. The number of regions is 1. And from this we can conclude that if the number of vertices is n, the number of edges is n minus 1, and the number of regions in trees is 1. And if we substitute the following into Euler's formula, we see that both the n's cancel out and we get 2 is equal to 2. Therefore, we can say that Euler's formula is applicable on trees. But what about graphs that are not trees? Let us look at them. For that, we can see proof number 2, which is induction on edges. For that, we first prove the base case, in which if the number of edges is 0, the graph only has one vertex and hence the number of regions is 1. Putting that into Euler's formula, we again get 2 is equal to 2, thus proved. Now, applying mathematical induction, we suppose that Euler's formula works with at most n edges. Now, taking a graph with n plus 1 edges, we see two cases. In case A, the graph doesn't contain a cycle, which means it is acyclic, which clearly hints towards it being a tree, as we have seen before that trees are acyclic, and that we have already proved. In case B, the graph G contains at least one cycle, which number of cycles may be more than that. And in that case, we pick an edge and remove it. This leads to R minus 1 and E minus 1 as V remains the same. And that just proves our formula. Thank you. Now I'm going to hand it over to Umama to explain applications of Euler's formula.
So the first application of the Euler's theorem is the Sylvester-Geli theorem. And the Sylvester-Geli theorem is that given any set of n greater or equal to 3 points of antipodal points on the sphere, not all on one great circle, there is always a great circle that contains exactly 2 of the antipodal pairs. When we use the Euler's theorem, we're able to give a proof for this but the arrangement of the great circle yields a symbol plane graph on S2, whose vertices are the intersection point of 2 of the great circles, which divide the great circle into edges. All the vertex degrees are even, and there are at least 4 by construction. Thus, the proposition yields the existence of a 4-vertex degree. Now, the second application is the monochromatic lines. And the theorem states that given any finite configuration of black and white points in the plane, not all on one line, there is always a monochromatic line, a line that contains at least 2 points of one color and none of the other. So the proof for it is as we transfer the problem to the unit sphere, and just like we do it for the Sylvester-Geli theorem, and we dualize it there. So what we must prove is that given any finite connection of black and white great circles on the unit sphere, not all passing through one point, there is an intersection point that lies either only on white great circles or only on black great circles. And when we actually transfer, we realize that since in every vertex where a great circle of different color intersects, we always have at least 4 corners with sign changes. And the last thing is Pick's theorem. So the Pick's theorem from 1899 is a beautiful and surprising result in itself, but is also a classical consequence of Euler's formula. So for Pick's theorem, basically to dumb it down, every polygon can be triangulated using the nth lattice point in the interior, and all the nbd lattice points on the boundary of Q. This isn't quite obvious, but when you triangulate, it is. And that is how there is a proof for Pick's theorem also. Thank you so much, and I hope you all learned something new.